So just by way of introduction, my name is Mike Balmforth. I was a student of Professor Eager's a few years ago. Before that, I did some work at Ohio State where I did a fair amount of research on the welding metallurgy of stainless steels. And so Tom has asked me if I would come and talk to you about stainless steels and the welding metallurgy of those today. So currently I work with Dr. Eager and with Dr. Belmar in a consulting group, and so it's nice to be able to work with them on a professional level and also to have the opportunity to come and talk to you guys a little bit about stainless steels today. So I wanted to start off by just talking a little bit about what is a stainless steel. So most of you probably, when you think of stainless steel, you think of this nice shiny silver metal that doesn't rust. And in most cases that's true, but stainless steel is not always stainless. There are things like sensitization, there are things like pitting, there are things like intergranular corrosion. If you mix up your stainless steel with your carbon steel and you get contamination, you can get rusting that way. And so as we talk about the metallurgy of stainless steel, we're going to be talking about things that could happen to that stainless steel to cause it to not behave like you want it to, which could be corrosion, could be rusting, it could also be cracking. There's a variety of things that can go wrong, and so we'll talk about some of those things. But stainless steel is based, at its very basic sense, is an iron chromium alloy. And then many of the alloys also have nickel in them. And there's always going to be a little bit of carbon and a variety of other elements that we will talk about. But the main thing that makes stainless steel corrosion resistant, or makes it stainless, is the chromium content. And that's because chromium forms a very tenacious passive oxide, or an oxide that protects the underlying steel. It's a Cr2O3 oxide. And so whenever that oxide is there and it's not nothing is wrong with that oxide, then your steel is going to be stainless. But if it gets a scratch in it, or if it gets a corrosion pit in it, or a variety of things like that, then that's when we can run into problems. But stainless generally is very resistant to chemical discoloration. And that's why it works great for your silverware and nice silver shiny instruments that you want to make and stuff like that. It's also generally very corrosion resistant. It's also got, in most cases, good high temperature oxidation resistance. There are a wide range of stainless steel types and alloys, so there's a wide range of strengths and ductilities. And it generally has pretty good fabricability, the ability to be formed and welded and other things like that. Next thing to talk about a little bit is classifications of stainless steels. Stainless steels are classified by their microstructure. And I hope that most of you have a basic understanding that microstructure is the structure. When you look at a polished specimen of steel under a microscope, you can see a variety of microstructures and phases and things like that. And the way that we identify stainless steels is by that microstructure. There are 5 different classifications that we'll mention today, and if we have time, we'll talk about 3 of them. I don't think we'll get to duplex and the pH stainless steels, but martensitic stainless steel is, just like it says, it's a steel that is mostly made up of a martensitic microstructure. The same with the ferritics, mostly a ferrite microstructure. The austenitics, which are the kind of the workhorse stainless steels, they're more used than the others, are a mostly austenitic microstructure, although when we get to talking about them, you'll see that we do like to have a little bit of ferrite in the structure. And then a duplex stainless steel is a stainless steel that is generally, typically about 50% ferrite and 50% austenite. And then the precipitation hardenable stainless steels are steels that are hardened by the strengthening precipitates that can form during heat treatment. A lot of people might tell you that you can tell if something is stainless or not by putting a magnet on it. And that's true for the austenitic alloys, because austenite, being a face-centered cubic structure, is not magnetic. But if you put a magnet on a martensitic or a ferritic stainless steel, it will actually stick. And so that's not always the way to tell. So I wanted to talk then a little bit about some of the different alloying elements that we end up putting in stainless steels. And they're broken down into two categories. One is the austenite formers, which promote the formation of the austenite, and the ferrite formers, which promote the formation of ferrite, which can then solidify as ferrite or even well, austenite formers actually end up being martensite, because when the austenite cools down, it can transform to martensite. But like I said earlier, the main alloying elements you'll see is chromium, which is a ferrite former, and nickel, which is an austenite former. And there's various other things that are attributed to each of these alloys and reasons that we put them in there. I don't think I'm going to take the time to go through each one of those individually, just because I've got a lot of information that I want to stress to you today. But if you're interested in that, it's easy to look that up in a handbook. So these various alloying elements that are put in the batch when you mix up a stainless steel lead to a steel with a certain structure, which then leads to certain properties, and you can use it for certain applications. And so it's very important to know what kind of a structure you're going to get and how to best use that. This diagram was developed a long time ago by a guy named Schaeffler. And what it does is it predicts the microstructure of a given stainless steel. And if you look at the axes, you've got a chromium equivalent along the x-axis and a nickel equivalent along the y-axis. And what they've done is they've taken the various alloying elements that you might find in your stainless steel, and they've basically what's the right word? Made them equivalent to either chromium or nickel. And so in doing the research to develop this type of a diagram, you have to determine, for example, on the nickel equivalent, that carbon is about 30 times more potent in forming austenite than nickel is, whereas manganese is about half as potent. And so you can use this diagram. You can take the composition of the steel that you're going to be welding on. You can plot it on these axes here, and what you'll find is that your alloys are going to fall in various regions depending on your composition. And so up here you'll have the austenitic alloys, and like I mentioned earlier, what these lines are here, these are called isoferrite lines. So this region over here is completely austenite, or it's 100% austenitic structure. But these lines here tell you that you've got maybe 0 or 5% or 10% ferrite in that structure. It's actually a good thing when you weld on an austenitic stainless steel that you get some ferrite in the material. It prevents cracking. Down here, this is where the ferritic alloys fall. The martensitic alloys fall over here, and you actually see that even in the martensitic alloys, sometimes you get a little bit of ferrite. That's actually where most of my research was in this region down here. I developed one of these type of diagrams for this martensitic to ferritic region. The duplex alloys, like I said earlier, are in here where you've got both ferrite and martensite. And so this and the diagrams that have been developed subsequent to this, which are a little more accurate, are very useful when you're welding on a stainless steel to be able to predict the kinds of structures that you're going to get and how those can be used. So, like I said earlier, stainless steel is at its very essence, it's an iron chromium alloy, and so what this is called a phase diagram. I believe Professor Eager may have showed you, or Simone may have showed you the iron carbon phase diagram. This is actually the iron chromium phase diagram, and what it is over on this side you've got 100% iron. And over on this side you would have 100% chromium, and everywhere between you've got, here you've got 50% chromium and the like. This axis is temperature, and so if you take a 10% chromium alloy, for example, and you come up through here, when it's liquid you're going to be up in the liquid phase. As it solidifies you're going to come down through an alpha, which is a ferrite phase, and then you're going to come right along here. And what you want in stainless steels is you want to be over far enough that you miss this, which is called a gamma loop. That's where that's where you end up with the gamma, or the austenite. And as you solidify, basically in order to be corrosion resistant, you want to be over here far enough that you miss this gamma loop as you're solidifying. I'm going to show you a few other diagrams. I'm not going to spend a lot of time on them. But maybe as we're talking about the specific alloys, we'll come back to them. So this is what's called a pseudo binary diagram. Basically, this is a diagram that is taken by holding chromium constant at 13%, and then you actually, if you have 3 elements, you can actually do a phase diagram that looks kind of like this, and they're actually 3-dimensional diagrams, so they're kind of hard to visualize in 2D. But what you can do is take a slice out of one of these diagrams, and then you get something like this for iron, chromium, and carbon, or you get something like this for iron, chromium, and nickel. And we'll use these a little bit later when we talk more about the specific alloys. So like I said, the austenitic alloys represent really the largest group of stainless steels, and they're produced in the highest quantities. This is why when people talk about stainless, you know, and they talk about it being non-magnetic, or they talk about the largest uses of stainless steel, you're typically going to be talking about austenitic alloys. And they're based on the iron, chromium, nickel system. So besides the chromium, you're also adding nickel to this system of alloys to produce the austenite. These are the typical compositions. You're always going to have that high amount of chromium to keep things corrosion resistant, and then you've got the nickel to promote the austenite formation, and then you've got all these other amounts of other elements that can be added to the stainless steels depending on the application and what you're trying to do. Just spend a couple of minutes on some of the standard austenitic alloys. The workhorse grade, or the one that you would probably see used the most, it's the most economical of the austenitic alloys, is 304. Oftentimes you'll also hear about a 304L, which is a low carbon version of the 304 stainless steel. There's a wide variety of austenitic stainless steels, but like I said, they are the most commonly used. 304 is kind of the centerpiece alloy, and it's the most commonly selected austenitic grade as well. 316 is probably the next most used, and it substitutes a little bit of molybdenum for the nickel. You have a question? Well, the sulfur actually, it almost acts as a lubricant in machining. I'm not 100% sure on the work hardening of that, but that would make sense, that it wouldn't work harden quite as much, because that is one of the problems with austenitic stainless steels is they're a little bit gummy when you're trying to machine them.
What is it about austenitic alloy that makes it non-magnetic, especially considering it has a lot of nickel in it?
Well, the nickel actually in this alloy system is an austenite promoter, and so the austenitic alloys they actually solidify with a face-centered cubic microstructure, which is a austenitic non-magnetic microstructure. So it's really just the austenite that's formed is a non-magnetic structure. Another one that I'll mention is both the 321 and the 347. They're what's called stabilized grades. We're going to talk a little bit about intergranular corrosion of stainless steels, and the titanium and the niobium that are in those grades will tie up some of the chromium carbides that would normally be formed, and they'll prevent some corrosion, what's called intergranular corrosion. So this is a diagram that Professor Eager actually gave me the other day, and what it is it's just kind of a diagram that demonstrates that 304, like I said, is kind of that centerpiece alloy of the austenitic stainless steels, and then depending on what you're adding or subtracting, if you're adding a little bit of molybdenum, then you come down here to the 316 alloys. If you end up adding a lot of chromium, you actually move all the way over to the ferritic alloys. The more nickel you add, the more closer you move to the nickel alloys, which we'll actually talk about in a few days when I lecture again. So the real essence of this is that the 304 and then various modifications of that are at the centerpiece of the austenitic alloys. Some typical applications for the austenitic alloys. They're really used in a wide range of alloy applications, but they can be used structurally. They can be used for containment. They can be used for architectural or kitchen equipment, medical products. One of the reasons that they're widely used is because they are fairly corrosion resistant, but also they're readily formable and fabricable. They're probably the easiest to weld on as far as the stainless steels. One thing that it is good to mention is that the austenitic stainless steels are not suitable for chloride-containing environments or highly caustic environments, because those are the environments that do lead to stress corrosion cracking and intergranular corrosion and other types of corrosion with austenitic stainless steels. Yeah, I mean, anything with chloride in it, I mean, it's really a problem where there's some kind of stress, but when you've got welding, you've always got some residual stress. And so we often find when something has cracked or there's been a problem, it's called stress corrosion cracking, and I think Professor Eager, if he hasn't talked to you about that, will be talking to you about that in more detail. But you know, if you've got stainless steel pipes under your sink and that's where you store your bleach, then you know, sometimes it can be a problem. Some things to consider when you weld austenitic stainless steels, because they don't precipitate or they're not hardenable, basically. There's no need to preheat them. And it is important because of the phases that can form that you do watch the inner pass temperature if you're doing multiple welding passes on the austenitic stainless steels. Again, because they're not hardenable, there's not really a need to post-weld heat treat on the austenitic stainless steels as well. You can stress relieve if necessary, but you need to consider the carbides that could form, and you need to consider sigma and other phases, which are brittle phases that can form in these alloys. Filler metals that are typically used in welding of austenitic stainless steels are either matching, or 308 and 309 are very common for welding on. 304, for example, because of the solidification microstructure that you end up with that has some ferrite in it, which is what we're going to talk about in a minute. You do. It's very important with stainless steels that you weld in an inert environment, because at high temperatures the chromium oxides form, you know, very rapidly, and you get what's called sugaring. You get this black oxide all over everything. So that can be done in a variety of ways. It can be done with shielding gas, where you blow gas through the welding torch. A lot of times you have to set up some kind of a backing gas system as well, where you're blowing gas on the backside of it. I used to work for a national lab where we welded stainless steel parts in glove boxes because we wanted to be very careful that there was no outside contamination at all. So next I wanted to talk about some of the issues that can arise when you're welding on stainless steels, and probably the biggest issue that you need to be aware of when you're welding on austenitic stainless steels is solidification cracking, which is basically cracks that form in the material after you've welded on it as it's re-solidifying. And what you find is that the fully austenitic alloys are more susceptible. And also impurity levels like sulfur and phosphorus, because when a material solidifies, those impurity elements actually, as the material grows together, they get transferred to the boundaries that are created as the material grows together, and they end up creating a low melting phase or a eutectic phase, which is much more susceptible to being pulled apart as the shrinkage stresses are created during solidification. So some of the things that you can do, you can try to minimize your restraint. You can watch your heat input. You can also use the right filler material, which we talked about. 308 and 309 are typically used. This is a diagram that demonstrates solidification cracking susceptibility of austenitic alloys. This is total crack length, which basically is a measure of how much cracking you get. You add up all of the cracks and add it together, and that's your total crack length, basically. This is a chromium-nickel equivalent relationship. This is where you would take something like those chromium and nickel equivalents that I showed you on the Schaeffler diagram, calculate those, and then divide the nickel equivalent into the chromium equivalent. And you'll see that when you get a value that's below about 1.5, you get much more cracking than when you're on the other side of that value of 1.5. In fact, you get a small region in here where you get very low crack susceptibility. And what this is up here, this region here, what this is telling you is this solidified as austenite. Gamma is the symbol that represents austenite. Here is austenite plus ferrite, or delta, and then this is completely delta, completely ferrite over here. And so in order to avoid cracking in your stainless steel welds, you really want to solidify right in this region right here, which is austenite with just a little bit of ferrite. And solidification behavior of stainless steels is actually something that you could teach an entire course on. So I'm going to try to go through it quickly enough, but in enough detail that I can give you some understanding. So when an alloy solidifies, you can use those phase diagrams that I showed you before. In fact, I'll put one up here in a minute. But you can either solidify from the liquid. You can either solidify as austenite, and then you can have some transformations in the solid state, or you can solidify as ferrite, and then as it solidifies, as it cools, you can have further transformations in the solid state. And so there's something called austenite solidification, or A-type solidification. You can get fully austenitic if you're far enough over on the phase diagram. If you're a little bit closer to the boundary, you'll still end up with a little bit of ferrite, and that's called AF solidification. Or you can solidify as ferrite, which then will transform, partially back to austenite as it cools. and that's called Fa solidification. And these are different types of ferrite that will be formed. Down here you get something called Widmanstätten austenite in a ferrite matrix. That's where it pretty much solidifies all the way as ferrite, and then at the very bottom, sometimes along the grain boundaries, you get a little bit of austenite that reforms, and that's called F-type solidification. So this is graphically demonstrating what I was just talking about. Over here is the austenite solidification, and the furthest one on the left is A-type solidification, where as you're solidifying from bottom to top in this picture, basically everything is transforming to austenite. The white is austenite, and you get a completely austenitic structure as it solidifies. If you're a little bit further over on the phase diagram, as you solidify austenite along the boundaries of those solidification dendrites, is what these are called, you do get a little bit of formation of ferrite, and that's called the AF solidification mode. And then these two here are the FA type solidification modes, where you're actually solidifying as ferrite, but then as it cools, you're getting a transformation. You're getting a transformation back to austenite, and what it leaves is this little lathy or skeletal structure of ferrite, basically at the cores of those dendrites. Something that you don't see very often in stainless steels actually is complete ferrite solidification, or F-type solidification mode. I'll just put these up here quickly. This is just to show you kind of how you get these phase diagrams that I was talking about earlier. If you had a iron, chrome, nickel phase diagram in 3 dimensions, this is kind of a two-dimensional representation of what that would look like. But what you can do is take a slice of that, and that's what's shown here. If you slice this off basically at 70% iron, which is a typical composition of austenitic stainless steels, then you can look at this surface here, which is exposed by making this slice, and then you've got this what we call a pseudo binary phase diagram, and here's where you see that over here you get solidification completely as austenite, whereas over here you get solidification completely as ferrite. And right in this middle region in here is where you get sometimes austenite and ferrite together, and so that's where most of our stainless steels actually fall, is in that region there. Something that was developed much later than the diagram that I showed you earlier, the Schaeffler diagram. This was developed by the Welding Research Council, so it's called the WRC 1992 diagram. And what they did is they modified these chromium and nickel equivalents, and basically this is the region between austenite and ferrite, so it's just a small section of that Schaeffler diagram. They also drew on here the solidification modes. So above this line here you get completely austenitic solidification, and you can then see the AF and the FA and the F-type solidification as well on this diagram. And what they've done over here with these isoferrite lines as well is they've changed to something called a ferrite number, which instead of being a percentage of austenite and ferrite is actually a magnetic reading. And so there are various readings that there are various instruments that can be used to determine the ferrite number. One is called a magna gauge. I think Professor Eager has one of those in his lab. Basically, you stick a magnet on there, and then you measure the force that's required to pull. So the higher the force, the more of the magnetic ferrite that's actually in in the material. And so in order to avoid cracking, like I said earlier, you want to really be in this FA type solidification range. And so as you figure out the chromium and nickel equivalents of the material that you're welding on, and you can also figure those out for the filler material that you're using, and then you can figure out where you're going to end up on this and whether you're going to be susceptible to cracking or not. There are other issues with welding of austenitic stainless steels, and one of them I wanted to talk about is intergranular corrosion, which occurs due to something called sensitization. And I think the easiest way to demonstrate that is with this picture here. Basically, when you weld on one of these types of stainless steels, you've got boundaries between the grains in your microstructure. And if you get this what's called intergranular corrosion, you get all these little corrosion ditches along the boundaries of the material. You can actually have complete grains that will just fall out of the material. The reason that happens is when you heat the material due to welding or some other reason, along the grain boundaries, you've actually got carbide precipitation that happens between the chromium and the carbon that's in the material. And when that happens, it leaves this chromium depleted region